Okay, in this session of the lecture, I'm going to introduce YouTube manometers, and then I'm going to solve 3 examples for determining hydrostatic pressures in different fluid applications, so that you get more familiar how you should use these hydrostatic pressure distribution formula that we learned in the previous sessions. Okay. So YouTube manometer is something like this. That we use for measuring is a equipment like this, or the instrument like this that we use for measuring pressure and so this is used, this kind of YouTube manometer is used for measuring pressure using a U-shaped manometer. So this is, if you see, it's kind of looks like a U-shape. So we use this kind of U-shaped manometers to measure pressure. Okay, so how do we want to do that? So what we have is we want to measure, PA, pressure at point A, right? If you want to measure pressure at here, okay, using this manometer, this blue manometer that looks like a U-shaped thing, right? So I'm going to use these rules that we learned so far about these incompressible fluids at rest. One of them is that if we move horizontally from any point to another, the pressure does not change in a fluid at rest. So this is the first rule that we are going to use. And then the second rule I'm going to use is this hydrostatic distribution based on the movement in the vertical direction. So if we move vertically in the vertical direction, this is how the pressure is going to vary, okay? So here you see that if I move in this direction horizontally, right, the pressure should not vary. So I can write PA, pressure at point A, equals to pressure at point 1. Correct? This is based on that rule. We have a fluid at rest. So this is the horizontal move. So pressure was not changing. And then our second move, I'm going to move through this manometer and then just calculate the pressures at each point, okay? The second move here we have is vertical move, right? We are going to move in the vertical direction. So let me just write it, show it here. So this is, let's say, X direction, and this is Z direction. So Z direction is vertical direction. So we are going to move vertically here. So I need to use the other formula for calculating the pressure, hydrostatic pressure in the vertical direction. So I can write based on this formula here, which was for the vertical movement. I can write that P2, the pressure at point 2, equals to pressure at point 1 plus this fluid, the pressure that is exerted by this fluid on top of point 2, correct? And this fluid has a density of A, right? So I'm going to use rho A there, because this is a fluid here. So let me show it here. This is this fluid. Okay, so P2 is gonna be P1 plus rho A, the fluid A, times G times this H1, right? The depth of the fluid from point 1 to point 2. It's a linear change. And then now we have an interesting thing, and that is if we move from point 2 to point 3, although we are moving like this, right, in the fluid, but eventually we have not moved in the vertical direction, but we only moved in the horizontal direction, right? So I can still write that, I can still use that rule that the pressure in a fluid at rest does not change horizontally, and I can write P2 equals to P3. Pressure at point 2 equals to pressure at point 3, right? And then I want to go to point 4. So for going to point 4, we need to go vertically again, right? So I need to use this distribution, hydrostatic distribution. So I'm going to write P3, pressure at point 3, is pressure at point 4 plus the fluid on top of that, which is going to be rho B. Now the fluid is changed from A to B. We have another fluid that is the fluid of the manometer that we know its density, times G times H2. H2 is this depth, right? It's this depth there. And then we have a move to horizontal move again to point B. Okay, so again the pressure at 4 and B are going to be equal based on this rule that we introduced before. Okay, so now you see the procedure, how we went from point A to point B using all these hydrostatic pressure principles, and how we can find PA based on PB, pressure at point B. Okay, so let me just simplify this and get a final pressure based on for A, because this is what we want to find, right? So from these all equations, I'm going to write down this. So PA instead of P1, I'm going to write PA here, right? I'm going to bring it from here, plus rho AGH1. This is going to be P2, which equals to P3, which equals to P4 plus rho BGH2, where instead of P4, I can just plug PB here. So I'm just going to use that, equals to PB plus rho B GH2. So now I can write PA. This was our unknown which we wanted to find. the pressure at point A, which we don't know what is that. For example, it can be a tank of any fluid like oil or anything or gas, and we want to measure the pressure in that using these kind of U-shaped manometers. So this is our unknown, which equals to the pressure at B of the manometer plus rho B GH2, which we know, minus rho A GH1. Okay. So this is an important formula. So all these procedures, I'm gonna introduce an interesting rule for which is known as Manometer Rule. If you learn it well, then you don't need to write all these equations again. So you can use this rule, which is gonna kind of facilitate writing these and make your life easier. Okay, so let me introduce that. So Manometer Rule. This rule states, proceed through the manometer. Manometer. Add raw fluid GH if moving to a greater depth or subtract if moving to a lesser depth. Okay, let's use this formula now. So I'm going to proceed to the manometer. So I'm going to start from here, this point, okay, from PB. So first I'm going to write down this PB. And then it says, add fluid if moving to a greater depth or subtract if moving to a lesser depth. Okay. So here, I know if I move horizontally, I'm not going to change anything, right? So this is going to equal to this one. So I just move from this point to PB. I'm going to move to P4. And then I'm going to a greater depth here, right? I'm going to a greater depth. So I have to add pressure when I go to point 3. So I'm just going to add rho fluid, which is rho B times G times H2, plus rho fluid, which is rho B GH2. Then I'm going to move from point 3 to point 2. I have not moved to any lesser depths or greater depth, so I'm not going to add anything. And then from point 2, I'm going to move to point 1, and I'm moving to a lesser depth, right? From greater depths to a lesser depths, right? So I have to subtract that from my pressure if I want to get the pressure at point 1. And now the fluid also has changed to rho A, in this direction, so I have to subtract it with row A. So I'm going to write it minus row A G H1, right? H1 is this depth here. And then I am moving again horizontally, so the pressure is not going to change. So this equals to pressure at point A. Okay. So compare these two equations together. They are the same. So instead of using and writing all these equations based on those assumptions we had and those derivations we had, we can use this manometer rule, which is going to make our life easier. So if you just follow this rule, you can solve a lot of examples very simply without thinking too much. So you can just say if you are going to move horizontally, the pressure is going to be the same. If you go to a greater depth, you have to add pressure. If you go to a lesser depth, you have to subtract that pressure. And the pressure is rho GH, rho fluid G times the depth that you're moving. Okay? So now let's see some examples. Let's solve some examples of this and see how this is applied in real cases. So the first example I'm going to solve is this. So example. So the question asks us to determine the pressure reading of the YouTube manometer manometer gauge. Okay, so we have a YouTube manometer gauge here. So this fluid, we have fluid here. This fluid is mercury. So let me show it. This is mercury. And then here we have different depths. So I'm just going to write their length. So H1 is 1 meter. H2 is 0.2 meter. H3 is 0.1 meter. Okay, so I think I need to write it down here again. This is H1. So this is H1, this is H2, and this is H3. Okay. And then the density of mercury is 13.56 times 10 to 3 kilogram per meter cube. And the density of oil, and here we have oil in this fluid, here we have oil, and here we have air. The density of that, the oil, is less than water, so it's about 881 times 10 to the power 2 kilogram per meter cube. Okay. So I want to find the pressure reading of this pressure gauge at here, right? So let me just change that. The pressure reading, it should be using the pressure reading of the pressure reading, of the YouTube manometer gauge. So I wanna find the pressure reading of this gauge here. Okay, so let's solve and see how we can do that, and I'm gonna use the manometer rule to solve this question. So answer. So based on the manometer rule, I'm gonna go through this YouTube manometer. So I'm gonna start from here and then go through these manometer until I get here. Okay, so first I have the atmospheric pressure here, right? So I'm just gonna write it down, P at atmospheric. And then from this point, I'm going to a greater depth, so I just need to add pressure. So I'm gonna add rho of mercury, G, H3, and then from here to here, the horizontal, there is no change in the depth, and I've just moved horizontally from here to here, so the pressure is not going to change. And then from this point to this point, I am going to a lesser depth, so I need to subtract pressure. So I'm just going to subtract rho, the density, and here I am in the oil, so the fluid has changed, so I need to use the density of oil. So I'm going to write rho oil, GH2, and then from this point to this point, I'm going to move horizontally again, so the pressure is not going to change because I am not going to a higher or lesser depth. And then from this point, I'm going to this point to the, let's say first to this point, the interface between oil and air. So I'm going to lesser depth, so I have to subtract pressure again. So it's going to be minus rho oil GH1, and then I get here, And so in this area, this is the pressure gauge area. So it equals to the pressure of air, right? So this is, I have used the manometer rule, and simply I was able to relate the pressure of air to the atmospheric pressure here and all these different components. Okay, so I'm gonna assume something. You can either use the atmospheric pressure, which is 10 to the 5, right? 10 to the 5 Pascal, and add it to this equation. Or this is what typically we do, and this is going to give us the absolute pressure of air, right? If we use the atmospheric pressure here. But we can neglect atmospheric pressure in most of the problems because it's the same in all the kind of calculations that we have. The atmospheric pressure is going to be there, so we can just neglect it in all of them and then get a relative pressure, which is relative to the atmospheric pressure. Okay, so we can assume, that means what is the pressure of that point with respect to the atmospheric pressure. We can assume that P atmosphere is the reference pressure for all the problems that we are going to solve from here on. Reference pressure. And so we can just neglect it and set it to 0. So convention relative to the P atmosphere, unless otherwise stated that you need to calculate the absolute pressure. So if in a problem they give you the atmospheric pressure and then they ask you to calculate the absolute pressure, you have to add it, and you should not assume that it's 0. Otherwise, we conventionally in this type of problems, because as I said, atmospheric pressure exists everywhere in all the problems, we typically assume that it's 0. The reference pressure is 0, and we just remove it from our calculations. And so the pressure that we are going to find is the pressure relative to the atmospheric pressure. So it means how much the pressure that we're going to find is the delta P, right? Shows how much pressure we are higher or lower than the reference pressure or the atmospheric pressure. Okay, so using this, I'm gonna calculate P air in this formula. So P air is gonna be P atmosphere, which I'm just gonna assume it's 0 based on this assumption here, plus rho mercury. Rho mercury is 13.56 times 10 to the power 3 times 9 G, which is 9.81, times H3, which is 0.1, right here. Then minus rho oil, which is 8.81 times 10 to power 2, times G, which is 9.81, times H2, which is 0.2 meter, and then minus rho oil, which is gonna be So one thing I can do, I can just, instead of writing this again, here I can just write it, just factor rho oil G, and then it's gonna be H2 plus H1, right? H2 plus H1 is 1.2, right? So I can just, for simplicity, write that. So instead of 0.2, I'm gonna write 9.81 times 0.2 plus 1, which is gonna be 1.2. And so if you calculate this, you are gonna get, from this term is gonna be 13,302, this term. Then we have minus 10,371. This is gonna be this term, which equals to 2,900 Pascal, or equals to 2.9, around 2,900. Around 2,900, which is going to be 2.9 kilopascal. Right? So this is how we solve this problem. Okay, how we have to approach this kind of problems. That is, we have to start using the manometer rule from one point and then just go to the other one. If you are going to a greater depth, we are going to add pressure, and if we go to a lesser depth, we are going to subtract this pressure until we get to what we want. Okay. So this was one example, and now I want to solve another example. And that is here. So the question asks, so let me write it here. So the question asks determine the pressure difference in terms of the specific weight, which is a specific weight is gamma, which we show is rho g, or gamma is the specific weight. If you hear that, it is just rho g of the flowing fluid. Okay, so here we have this flow. So here we have kind of a pipe, and then we have 2 points. One is point A and one is point B. One is point A here, and one is point B. And then the question asks, determine the pressure difference between PA and PB in terms of the specific weight or gamma rho g of the flowing fluid. Okay, so the fluid has a specific weight, which is gamma, right? And we want to determine this difference between A and B based on this specific difference, specific weight of this fluid. Okay, so in the manometer rule, instead of rho g, we can just use instead of rho g h, we can also write gamma h. This is just a note because this is the same thing. Like instead of rho g, we are gonna just call gamma, which is the specific weight, and write gamma h. Okay, so this is gonna further simplify the manometer rule. And so I'm gonna start from the manometer from here, from PA, and then go here, here, here until I get to PB. Okay, using the manometer rule. Okay, so let's start. So first I'm gonna start from point A, and then from point A I go up. So here we have this gamma 1, which is for the fluid. This is gamma 1. Again, here we have gamma 1. And only here we have gamma 2. This is another fluid, right? So here we have gamma 1, and then there we have gamma 2, and then the other place we also have gamma 1, right? This is all fluid. We only have another fluid from here to here, this place, okay? So I'm gonna go from point A to this point, which is H1, right? I am going to a lesser depth or a greater depth. Think about it. I'm going to a lesser depth, right? I'm going upward. A is deeper in the fluid compared to this point. So I have to subtract, and also you see the pressure at here should be greater than the pressure at here, right? So I have to subtract the pressure gamma 1 H1 when I get here to get the pressure at that point. So I'm gonna subtract gamma 1 H1, which is just gamma 1 is rho g H1. Instead of rho g, I'm just writing gamma. Okay, gamma 1 H1, and then from here to here, I'm going here. So I am not changing any depth. The depth is the same, so I just have moved horizontally. So I don't have to change anything or add or add or subtract anything. And interestingly, very interestingly, even from here to here, although the fluid is changed, but because I am not changing any depth and I just have moved horizontally, I have not gone to a lesser or a greater depth. I don't have to add anything to my pressure. But from here to here, I am going to a lesser depth again. So I have to subtract the pressure of fluid in this point. And now I am in the second fluid, which is gamma 2. So I have to use its specific weight, which is going to be minus gamma 2 H2. And then from this point to this point, again, I am not going to a higher or lesser depth. I have not moved vertically, and I have just moved horizontally. So I'm not going to add or subtract anything. And from this point to this point, I am going to a greater depth, right? So I have to add pressure. And here I am in gamma 1, again, the flowing fluid. So I add gamma 1. But what is this depth? So this depth is first up to here is H2, and then from here to here is H1, right? So let me make it clear here. These are not given in the problem, but you are expected to find this yourself, and you can find it from this geometry easily. So from here to here is H2, and from here to here is H1, right? Simply just by plotting a straight line, you can get that. So it's going to be gamma 1 GH1 plus H2. And this equals to the pressure at point P here. So just note, I have seen that some students may forget this H2 here, and then they just write H1. Okay, so this is important. You know, you have to look carefully at your geometry to be able to get the exact and correct pressure. Okay, so we have used these U-tube manometer rule to get the pressure from A to B. And now the question wants to determine this pressure difference in terms of the specific weight. So the pressure difference between A and B is as follows. So PA minus PB equals to, I'm sorry about this. I made a mistake here. There is no G here because we already have G in the specific weight. So this is going to be gamma 1 H1 plus H2. So we are going to have H1 plus H2. I'm going to factor it out from both of them. So I have gamma 1 minus gamma 2. I'm sorry, these two terms are going to cancel out. We have gamma 1 H1, and we have gamma 1 H1 here. So these are going to cancel out. So we are only left with H2. I'm going to factor H2, and then it's going to be gamma 1 minus gamma 2 times H2. Okay. So I just want to give you a physical sense. What does this mean? This means that in a fluid here that flows from in this pipe, we have a nozzle here. Okay, we have a nozzle here, as you see. And this nozzle, as you see, is going to cause some velocity decrease and also some pressure drop. So the pressure, the incoming pressure here of the fluid is high at point A, and then at point B, it's kind of decreased. And how much this decrease is gamma 1 minus gamma 2 times H2. This is how we can measure this rate of decrease, okay? So we'll learn the nozzle creates this pressure drop. In the fluid. Okay, so this nozzle causes, so the pressure at A is going to be smaller. It's going to be, pressure at B is going to be smaller than the pressure at A. Okay, and the rate and the rate it is smaller is written here, which is gamma 1 minus gamma 2 times H2. Okay, so this manometer, by just putting a manometer into this kind of fluid, for example, if you have a pipe flow and then you have a nozzle and you want to see how much pressure drop you have in this system, what you can do is you just install this kind of U-tube manometers before and after the nozzle. Okay, you know that a specific weight of or the density of the flowing fluid, for example, is oil or water or whatever you have, and then you also know the density or specific weight of the fluid that is in the U-tube manometer. And then you have all these measurements that you can make, like H2, H1, you can just observe them and measure them in the U-tube manometer. So you have all these values and you can simply calculate the pressure drop using these instruments. Okay. Okay. So final example of this part before moving to the next part, which is hydrostatic force on a plane. So, example, find the pressure in B for this inclined tube manometer. Okay. So interestingly, here we have an inclined tube manometer, and the theory is the same. It doesn't matter. Like if it is inclined or not, the principles that we had is the same. That is, if you move horizontally, the pressure is not going to change, and the only thing that matters is moving vertically. Okay, so the pressure at A is given. PA is 8 kilopascal. And the other specific things we have here, so we have water in this side. Let me So we have water in these two tanks. And then in between we have another fluid, rho m, which is shown here. Okay, so and now we have these all specification, these geometries. Okay, 0.1 meter, 0.3 meter, and 30 degree, and this is 30 degree inclined tube manometer. Okay. Okay, so let me now solve this using this the same YouTube Manometer rule. So I'm going to start from PA. It wants a pressure at point B. It's clearly given in the problem. And they have given us the pressure at point A, so we have read it. Okay, we know it. So I'm just going to start from point A, PA. Then I'm going to move horizontally, so the pressure is not going to change here. Then I'm going to go from here to here, so I'm going to go to a greater depth. So I have to add pressure. So I'm just going to add plus rho water G 0.1 meter, right? Then I'm going from this point to this point, and after that, I'm gonna go also higher in depth, okay? So I might have not, I think, plotted it correctly. So this water should come a little bit below that, so it should come somewhere around here. It is on the same, or let me maybe just do it from here. I think this is a better thing. This is gonna be from around here. Around here to here is 0.3 meter. And then from here to here is 0.1 meter. Okay. So these two are on the same horizontal and the same vertical distance. So from here to here, I am not changing anything. From here to here, I just moved horizontally. Okay. And only from here to here, I have moved vertically from this point to this point. So I'm not going to add from here to here. I'm not going to add anything. But here, from this point to this point, I have moved both horizontally and vertically, right? In the inclined tube. But the only thing that matters to me is not the horizontal distance that I've moved, but the vertical one, right? So this doesn't matter. How much I've moved here, it doesn't matter. From here to here, it doesn't matter. But the only thing that matters is this much. And what is this? How much I moved vertically, and I have moved to a lesser depth, so I have to subtract that, right? And how much is this gonna be? So this angle is 30 degree. And then this length is 0.3 meter. And so from very simple geometry, you can say how much this is gonna be. This edge is gonna be this 0.3 meter here times the sinus of 30, right? Why? Because the sinus of 30 is defined as this h over 0.3 meter, right? You have a triangle here, so let me show it more clearly here. So you have a triangle here. This is 30 degree. You want to know what is this h, and you know this is 0.3 meter. So the sine of 30 is defined as h over 0.3. So h is gonna be 0.3 times sine 30. Okay? So I have to, because I'm going to a lesser depth, I have to subtract that. And this is another fluid, which is M. So I'm just going to use its density. So it's going to be rho M G times 0.3 times sine 30. This is the h here that I'm moving this direction. Correct? And then from here to here, again, I am moving both horizontally and vertically. The horizontal direction doesn't matter, but the vertical depth that I'm going to a lesser depth is given in the problem. It is given as 0.1 meter. So I'm just gonna subtract that as well. So rho water G times 0.1. Okay. So this is important because here, if you see in the problem, for this one, we have the problem gives us the vertical depth. So this has kind of made our life easy. But for this one, they have not given the problem has not given us the vertical distance, but it has given the whole both horizontal and vertical one. So we have to decompose it into the vertical direction and only find the vertical direction by vertical distance or depth by geometry, by using geometrical kind of relations. Okay, so now I got here, and then from here to here is a horizontal move. So the pressure is not going to change. So this pressure here equals to P at B. And this is what we wanted to find from the problem. Find the pressure B for this inclined nanometer. So we have all the values of this, and so we can just substitute and find pressure B. So I'm just going to write it down. So PB equals to, first, these two terms equal to each other, so they are going to cancel out. Raw water G 0.1 meter. So we didn't even need the raw water in this problem. So sometimes there might be some kind of these tricks. We don't give you the density of water or density of any fluid, but because they are going to cancel out, so they don't really matter. Okay? So this is going to equal to PA minus rho m, which is 3 times 10 to the power 3 kilogram per meter cube, times G, which is 9.81, times 0.3 times sine of 30, which is going to be 1/2. These all equal to if you calculate it, this is going to equal to instead of PA, you need to write 8 kilopascal. And this is going to be 4.41 kilopascal. So finally, we are going to get 3.6 kilopascal. So this is going to be the pressure at point B. So we were able to find it by using this simple manometer rule that we explained. So this is a very powerful rule that you can use it in all these kind of hydrostatic problems. And after this, in the next session, we are gonna talk about the theory for the hydrostatic forces on the plane, especially for inclined planes, which are going to be important. And in the next lecture, we are going to solve some examples of that. And after that, we are going to work on hydrostatic pressure force on a curved surface. And this will be mostly the kind of the end of, and a little bit about the stability, and that this will be the most of the fluid statics. And after that, we are going to go to the next topic, which will be Bernoulli equation and fluid dynamics. Okay. So let me briefly review what we did today. So we just introduced the manometer rule, which is by measuring pressure using a U-shaped manometer as shown here, where you can move from through the manometer from one side to another based on these hydrostatic distributions that we discussed before. And then if you proceed, you need to proceed through the manometer at rho fluid GH if moving to a greater depth, or subtract if moving to a lesser depth. Okay, so you can get this formula that is shown here. Then we solved 3 examples. So one was a simple one where we had this U-tube manometer gauge, and then we wanted to find the pressure at here. So we started from the atmospheric pressure free surface, and then wrote this manometer rule, and we got that. And we mostly, as I said, we assume the atmospheric pressure reference is 0 unless it's given in the problem. So if the atmospheric pressure is given, that means you need to account for that, you need to consider it, and also you need to calculate the absolute pressure. And it's, for example, if the problem 6 wants us to solve and calculate the absolute pressure. And then we talked about we showed and solved another example, which was the pressure drop in a pipe flow, again using these manometer, U-tube manometer here. So we started from one side and then moved to another side, used this manometer rule, and we were able to find this pressure drop PA minus PB in this problem. And finally, we solved this problem for an inclined manometer. And it doesn't matter, again, for inclined manometer, it is inclined or not. The only thing that matters we found here is the vertical direction. Okay, so if any problem they have given us this length, we just need to calculate this edge here, which is how much we have moved vertically, and that is how much we have to kind of add or subtract from our pressure to be able to get to where we want. Okay, so it doesn't mean how much we move horizontally. This can be like a very long thing or small in this kind of hydrostatic fluid problems at rest. And the only thing that matters is moving vertically. So we started from one point here, then we just went this direction to get to point B, and we wrote the manometer rule, and also we used some geometry relations as shown here. Okay.